Hi everyone, and welcome back. So in this session, this is an open discussion with Alessandra and Arkady, and you're welcome now to ask as many questions as you want to the speakers about their talks and beyond. Is there any question? And we will use the rule as in the previous days that hand is new question and finger is follow-up.
Alessandra. So I'm always a bit puzzled with this computation of the page curve because you see, people say it's a semi-classical computation, but somehow when they say that the curve basically has this behavior and goes to zero at the end, going to zero at the end means basically at the end of the black hole operation, nothing is left where the black hole was, and everything has gone in the irradiation. So very often people say to really understand what is the endpoint of black hole evaporation, we don't just need to go beyond semi-classical black reaction, we really need most likely some quantum gravity understanding because we are at the end of the evaporation. For instance, it could happen that you form some small remnant or whatever, anything happen. So just by looking at this page curve behavior that they claim to derive, it seems like that they can even answer the question of what happens to the end. So what happens at the end of the black hole evaporation? Because just by looking at a curve, nothing is left. But still, you are in a semi-classical regime, as you said, when you do this computation. So, is it really true that we can trust the last part of the curve?
I don't think it's claimed that their computation hold or like it is believed that string theory captures this curve in the evolution of states that are built in string theory. But when you do these computations, you're after the page curve, but not completely in a quantum black hole regime. So you're saying that you capture the turn of this curve, which is still highly non-trivial. And then there is, maybe you have to go in fully stringy regime to describe what happens at the end. So your state will be maybe a state of interacting strings at that point. Or there is also this point where there's this black hole, black string correspondence that maybe you hit in the evolution. But that is not the point of those calculations. The point was just to show that something which is order one different than the Hawking computation is present in your description of the system. And so this principle of extremizing surfaces, it's a principle that is defined in the effective field theory, doesn't require AUV completion, and gives somehow a result compatible with the fact that the page curve turns. So no one argues that.
The message you should take from this holographic computation and say is that at some point there's a turn, consistently, let's say, with area law and inequality, so but we cannot really trust this computation until the end. We should just cut at some point and say, okay, there's a turn, and then we stop because semi-classical.
Yes, it answered the question. What does this regime? What is this regime described by? And I think that what we learn is that quantum extremal surfaces play an important role in gravity, or like in our understanding of quantum systems, way beyond what Ryuta Kayanagi told us. Like Ryuta Kayanagi was a prescription to compute entanglement in the CFT, and it first identified some extremal surface that played an important role for quantum fields. And if you push that in a full quantum regime and you extend it, then you figure out that understanding quantum extremal surfaces is of fundamental importance for your system. You can't neglect them. And so the refinement of this entropy computation by defining a generalized entropy that takes into account a part that is this area law, a part that is the bulk entropy, the extremization, like how to obtain this extremization. Somehow the consistency of this definition is seen by the page curve. So it correctly reproduces these parts of the page curve, and so we've produced a correct prescription and an important entropy. And then there's many more. Then the questions start, right? It's like, oh, what is the gravity meaning of this? And that's where warmer computation start, and how general it is. Can I extend it to higher dimensions? So it's even just at that level, there's a lot to understand.
Follow-ups on that?
So, I mean, I think the statement is correct. This curve beyond certain point cannot be trusted. And so you probably see turnover. Well, even turnover, I don't know whether I mean, certainly it makes sense that this entanglement should reach the maximum. But entanglement between outgoing radiation and what remains. But then there are other effects that, for example, this curve is not must be taken into account into this curve, which, for example, usually are other effects like there is, for example, there is inner entanglement.
And this will go beyond the semi-classical.
Of course, yeah. These are
absolutely.
These are physically constant. So yeah, so it must be
goes constant.
They usually show the full universe.
I don't know why. I've never seen any trustable computation that can really take you over the top. So another thing is that, I mean, you can ask this question. I mean, how much of string theory do you really need to understand this curve for a macroscopic black hole? I mean, probably it's understandable without string theory. I mean, the computations are much heavier than the energy involved in the process. Why should string integration partners?
Okay. Any follow-up or other questions? I mean, Arkady and Alessandra were already discussing
No, he was
something.
pointing out that
Maybe you.
it's off. That in many explicit computations, what you get is not even the turn down; is a plateau, like it's a stabilization of entropy at a certain point, because of your toy models, like and also. No. It's just like your models, like when you compute these islands, they have they saturate a certain entropy, and that's it. But also there's many caveats, like for example, in higher dimensions, there's in order to satisfy this construction of the ADS black hole that leaks radiation, somehow you have some non-conservation of the stress tensor that pushes as slight massive mass for the graviton, and so it seems that you're actually modifying the theory. So it's a question of like how much you can trust it. But again, I would like to push in the direction of the prescription that is given, right? This generalized entropy, the role of these quantum extremal surfaces is something that's emerged. And it has to do with the structure of entanglement for fields on a curved background, which I think we don't completely understand. And even I agree that like the black hole solution we're dealing with at some point, which may be way before we reach the string scale, is no more the semi-classical black hole we believe in. We were dealing with, but so the point is, what can we quantify that makes sense in a certain regime? And so these quantum extremal surfaces capture something, and we may not know what that something is. We need to characterize it. We need to understand its properties, and that's for me a very interesting angle on research on what does it mean to have a semi-classical black hole evaporating.
I have a small follow-up question on this. So I mean, recently, but it sort of we understood that there is this sort of, we call it memory burden effect in black holes, meaning that it's not only in black holes, actually it's universal. If you have a system, which stores information in an efficient way, like black holes do, then it turns out that there's this universal effect that the information load, not the information capacity, but the information load tends to stabilize the system. So somehow once it reaches and again, the latest time comes out to be K's time. I don't know why, but it's like probably there's a good reason for it. But it's like half, when the system loses half of its approximate mass. So latest by then, this memory burden effect tends to stabilize the system. And this is, I've never seen any exception. This it turns out to be universally true in every system in which you can do computations. This is what comes out. So presumably similar things should happen in black holes. Presumably, I mean, okay, for black holes it's not easy to do computations, but since the effect is universal, so and it would be interesting to see whether this technique, for example, that you were describing, that could somehow capture this effect. I don't know what should be done, but it would be something interesting to check whether it is there. I mean, it would be miraculous if it's not there, but still would be interesting to see some of it. It's just a wish. I mean,
yeah. It requires more discussion, more details, but I think that's exactly the way we should ask questions about this. Is like, okay, if we have a new prescription, what can it tell us about the system that we didn't know how to compute before? Or yeah, and there's also many I mean, there's a lot of research recently also on like 2D, 1D holography. There's models like SYK where one can really, it's a one-dimensional model, but one can do many numerical computations. And so this is not just one way to approach the study of quantum black holes. There's many behaviors that can be captured from different angles. And so I think the point is to really try to answer different kind of questions. And so, yeah, maybe I'll ask.
Can I ask the following question? So can we completely decouple this story from UV? For example, there were discussions that actually the near horizon, this firewall, etc., which suggests that you cannot really ignore UV effects. So here you kind of pretend you don't care. But indeed, there is an issue, for example, do you need to include, so suppose we embed this into string theory, there is a Schwarz solution, but in principle it's modified by alpha prime corrections, and maybe in some exact treatment there's no singularity, maybe, but it's very hard to make this precise unless you find some exact BPS, whatever solution, which is not modified, etc. But that problem of evaporation, you may pretend it's unrelated to that because we consider a large black hole and we don't care about alpha prime corrections. But could there be some loophole in this argument? Yeah, I'm just trying to.
I think the problem people had with the description of black holes is that there's no parameter that tells us that some corrections becomes order 1. Apart from these argument about looking at entanglement. And so why should we have these effects in the semi-classical theory? So we can start using entanglement and to quantify how quantum our state is. And then if that reaches order 1, then okay, then we are away from the hypothesis of the semi-classical theory, and we need to modify it. And that could be one way of guiding our principles. And then we can be like, okay, in this new regime, what does it work? Does this computation work? Do we need to modify something? They do not claim they solve the information paradox. I think the problem of the structure of entanglement is still there. Like so, Matour's objection or a firewall paradox is still there. But this computation assumes that as a semi-classical observer, you can look at a black hole from outside and follow its evolution from the outside without like running into issues, at least up to order of page time. And that was somehow the semi-classical point of view is underlying these constructions. But yes, for me, there must be a new order parameter that tells us that something goes wrong, and maybe entanglement is playing a bigger role than we thought in quantizing fields on gravitational backgrounds. Could it be?
Maybe Mariana, if you read that paper, so there are some subtle effects about horizons related to effective field theory. So that's another indication of something may be going wrong in some models. Could you comment on that?
So there's been a few papers. I guess they started with by Santos 4 weeks ago, and they started doing black holes in ADS and seeing what would happen if you had corrections from higher derivative terms, either if you had Einstein-Maxwell, just a Reitner-Nordstrom, or if you had a Kerr. And they saw in many cases, and it even happened in ADS with just a scalar field. When you do higher derivative corrections, things will immediately break down. Perturbations, static perturbations around the horizon will be unstable. Then you have instabilities that just arise by adding higher derivative terms. And this also happened in flat space. And I think it's probably a question of interpretation of what's actually happening, if it's just perturbation theory breaking down, if it's effective field theory breaking down. But just immediately adding higher derivative corrections to gravity can change a lot of near horizon in the external black holes.
I guess my point is that it could be that if you embed this Schwarzschild into some UV, whatever, complete theory, which has some sensitivity to these high derivative corrections, maybe that problem actually has some sensitivity to UV. But of course, it's naively looks like that should not be the case.
Yes.
But yeah, I mean, following up on that, there are also some papers by Grant Remnen on these amplification effects of higher derivative. Oh, is this okay? Sorry, I did not remember the other orders. Okay, but those papers focus on black holes near extremality, and that should be a regime that is already away from a semi-classical regime. No, I mean, to reach extremality, you need to.
I think the Kerr, there is also another example. You need some curvature.
You need to be either a curved black hole or right there, Nordstrom black hole, but they do need the near extremal.
Oh, you need the near extreme.
Yeah, exactly. This is the point. But if you have a large black hole like that is not near extremality, can the horizon still affect the effective field theory or the higher derivative corrections? So if you are really in a regime where you would, in principle, trust the effective field theory. Okay, yeah.
So your argument would be that the semi-classical translation is just not valid there?
No, I don't want to say, I mean, I'm just wondering if horizons can affect any way like the effective field theory expansion. Because, I mean, we have the example of near extremality where these calculations show that effective field theory corrections become important. But what about large black holes? There,
Extremality doesn't tell you whether black hole is small or large. Extremal black hole can also be large.
yeah, I mean, in principle, yes, that is true.
All you need is the charge mass.
Yes.
But then if you have an extremal black hole, which is galactic size, how can high derivatives affect it? The curvature is so tiny.
Yeah,
I would say that you can completely ignore any high order correction.
Yeah, you're right. You only need the extremality condition, and then you can have a black hole which is as large as you want. But these calculations show that near extremality, higher derivative corrections to Einstein-Hilbert are really amplified.
No, this has to do with null, kind of null components, which are important. Well, I don't remember the precise mechanism, but it is important that certain perturbations can grow once you.
That's very interesting, but that's also pretty shocking, right? Because I mean, it normally we say that what matters are the curvature invariant, and those are very small.
Yeah, exactly. It's like PP wave where you have large tidal forces, but you don't have curvature invariant. You can have R plus whatever I plus.
Full order, you don't have anything full order. Some invariants that blow up, right? Or not?
No. Scalar invariants are fine. It's just perturbations which are sensitive to the curvature.
Okay, that's pretty.
Yes.
Yeah, but
weird.
maybe there is one thing that,
Okay.
yeah, however, there is one thing that enters into the arguments that is using black hole perturbation theory, which, I mean, in principle, you would assume that it is trustable, like as you have large black holes. But it is one computational use that the computational tool that they use. So maybe something could go wrong in that. The way they construct the solution is by assuming that the parameter that enters the action, the couplings, are also the same small parameters that affect essentially linearly the corrections to Schwarzschild black holes. And well, I don't know if that is justified. I personally did not understand that, but maybe something can go wrong. But you know.
No, I think the short answer is that this needs to be studied better. And there was a recent paper by Claudia de Ram and the others, I think a couple of days ago. And I think it's still not the last word in this story.
What does that paper say?
Oh, well, they try, I think they, again, Mariana read it, but it's about applicability when whether you can trust effective field theory or not.
So sorry, but I got very intrigued because this is something very unusual. Because what is the control parameter? Because naively I would say, I can even say
it should be distance to extremality or some parameter. Yeah, I think it should be related to distance to extremality, something.
Because we can do the following thought experiment. We can construct the extremal black hole, which is very large, and then take the limit when it becomes infinite, and it becomes Minkowski in that case. The metric controls Minkowski, right? And then with that logic, you would say even Minkowski could not be. So there must be something that
No, but there is. It's again, it's extremal. It's not pure Schwarzschild. You need to have rotation or you need to have charge, and then you balance.
But it's not true that even for the extremal, if you take it very large, you approach Minkowski, right?
Oh, we need charge in that case, right?
Yeah,
but you take infinite charge, infinite mass, but
then you'll have, if you have infinite charge, you have lots of back reaction, presumably. No.
So you are saying it's not approaching Minkowski, even if because I make
probably physically it will not work. Yeah, it will not. You will not approach.
There is a follow-up.
But yeah, I mean, like this whole black hole stability, I mean, in math GR, this is now like quite well understood, and like that extremal horizons are unstable is about as old a story as you can tell.
But these are, it's just a pure Einstein, but this is about higher derivative corrections for that.
Sure, but it's already unstable in pure Einstein.
so you're saying they're unstable already?
Yeah. Extremal horizons are already pure Einstein.
But sorry, I thought it was the other way around. Now I thought it was people. I thought the extremal were the ones that were stable.
No, it's not extremal. Very small. So what is known is the theta small a is stable. Flat space, there's a claim that small a is stable. And the theta, there's one gap in the proof.
No, I mean, Minkowski, who is A? You said A, small a.
Small a?
What is called A?
Asymptotically flat small a is known, and asymptotically flat, and the theta small a is also known. And the theta is the rotation.
So slowly spinning.
So spinning black holes, the extremal is unstable, you're saying.
So this is so you see linear perturbations blow up on the horizon, yeah.
But which, I mean, so if you are not on the extremality condition, so it is the inner horizon that creates problems. So now you're saying, as you place them together, then
that's the at the end of the day, the surface gravity is 0. So what you have in a sub-extremal black hole, it's a competition essentially between the redshift and some other effects of the perturbations, and the redshift disappears when you go to extremal horizon, so things blow up. This is like it's standard. I mean, this is.
So you're saying basically then extremal black holes are unphysical, basically, because it doesn't make to think about them as the ground because they're unstable.
Yeah,
And this would solve the problem. Right?
Well, certainly doesn't happen in supersymmetric context. If you
I mean, this is just the linearized result, right? So it's the full non-linear instability that is not.
Yeah.
Sorry, is it just for extremal or for near extremal?
No, it's just for extremal. You have to be extremal. Like, I mean, the conjecture, black hole stability conjecture is that if you start with data close to sub-extremal black hole, it will stay within the sub-extremal time.
Because I think
It is then two different classes, yeah.
these ones are near extremal.
Okay.
Extremals, they would be safe.
Yes. Yes.
I mean, it is really indeed true that there is this some open questions about extremal black holes because about how to produce them. For example, if you want to produce them as an S-matrix process or something. So there are these open questions. Maybe it's related with what you're saying that they are, I don't know.
I mean, there is now, okay, this is, I haven't followed up on that, but somebody told me they're working on a result to show that you can start with a sub-extremal black hole and there exists a perturbation that leads you, like you can carefully construct it that you're walking into a extremal asymptotic state.
So you can project, no problem.
This is classical GR. Well, I mean, I haven't heard. I mean, this was a pre-announcement of a result in a private conversation, so I don't know how far that is.
I think this effect should be different from what Horowitz et al. Was saying, and Horowitz is certainly available. He knows about this story, yeah. So it should be different. It's complementary to that, and it's about this effective field theory. So once you add these high derivative terms, you get sensitivity to them. That's their claim in the near extremal limit. But anyway, it would be worth studying.
More questions? I have questions for Alessandra. So in at least a couple of statements that you made, so in particular, making some black hole constructions where in principle you would have ab initio like some dependence on the moduli configurations, but then you say you can get rid of this because of supersymmetry. And then supersymmetry also helps in other context because you can, in this specialized setting, reconstruct the black hole entropy from microstate counting. And my question is, if supersymmetry is not there, to which extent these arguments can be generalized without it, or go through in general?
So the
but I mean, if
microstate counting works can be trusted in a near extremal limit, let's say, and one can prove that the same counting works, although there should not be a protection of these number of microstates if there's no supersymmetry. In the context of studying the solution to try to trace what happens in moduli space or like in the breakdown of the EFT, one can use finite temperature black holes, so supersymmetry there is not really an issue. But if you want to do microstate counting, etc., then you do rely on supersymmetric solutions, like because that's where you can compute things, and that's where you know you're computing things that are protected in in holography. You just have a precise dictionary and you can compute thanks to, for example, supersymmetric localization. You can compute things precisely in the CFC side, just if you have supersymmetry.
But it is more like at a technical level that makes things easier, or at the conceptual level you
No,
would
at a conceptual level, ADS CFT are an exact duality. So if you were able to trace the thermal states in the CFT, in the brane construction, then you would be able to say, oh, these are the states that make the black hole. But it's really hard once you go away from the supersymmetric limit to understand, to understand what exactly those thermal states are. I think.
Yeah, the unfortunate truth is that it's very hard to get some precise information about anything thermal from unequal force theory. For example, free energy. We can compute finite temperature finite temperature, say gas of gluons, and then there is transition to kind of entropy going as not n squared, but order 1, which would be kind of effective confinement phase. But if you look at just this coefficient of n squared, it should be function of Toft coupling, just planar limit, in planar limit. And that function, it's known how it behaves at strong coupling, at weak coupling, but how it interpolates between is not known. And that's one of open questions, big open questions. So like what I mentioned, computing these anomalous dimensions in planar limit, you can do this. But computing this free energy in planar limit, we don't know how to do that. So finite temperature is a big open question. So black holes will be pushing this even further away from just this phase of gas of gluons, gas of elementary gluons. Yeah. Anyway, it's just side comment.
Okay, thanks. Other questions?
For Arcanis, well, I don't know anything about ADS-CFT, just a general question. So let's suppose that our universe is four-dimensional and that's negative cosmological quantity. So you would imagine the bulk some ADS is four-dimensional. If we assume this, is there anything known about the corresponding three-dimensional CFT?
This is a kind of question which needs some proper formulation. Yeah, naively you would say, okay, I have ADS that suggests that there is some kind of way to describe some things in terms of boundary theory. And we know that in the bulk we have Einstein theory plus some matter, etc., etc. So what that means is that in some regime where you can trust this classical theory in the bulk, you can compute some analogous matrix, or what would be correlation functions in the boundary theory. So you have ADS. In ADS, you can compute the analogous matrix, just specifying boundary states, like what you do with plane waves. And that computes certain correlation function in the boundary theory. But yeah, you can do that computation. You will get some prediction of what these correlation functions should be. For example, what's the correlation function for four stress tensor operators, which are dual to graviton? So if you consider class with these boundary conditions, that will give you a prediction about stress tensor correlation function at the boundary. That would be in some limit, which would be like strong coupling limit. And that's it. So you can reconstruct certain data about boundary theory, but you don't really know what you're talking about. It's just purely based on symmetries and boundary conditions and correspondence. But can you push this beyond that statement? That's an empty question. The other way, no. From the other side, we know which kind of boundary terms, well, like what I discussed is ABGM theory. It's like some three-dimensional Chern-Simons theory, which is CFT, which is superconformal theory. And then its bulk is starting with supergravity in, say, depends on which region, but say supergravity in 11 dimensions or in 10 dimensions in different regime with specified matter. And that's not like standard model, but it's some abstract supergravity. That's it. So that here you can actually push this far away. You can make it precise statement. But that's a very specific three-dimensional theory and very specific theory in the bulk. But if you try to invert this, yes, you may say, okay, whatever, standard model coupled to Einstein theory, that's defines some CFT, but that's not UV complete theory in the bulk. And it will not really tell us much about this CFT. It will tell us some correlation function of the CFT in some limit. And how do we know what happens beyond that limit?
Can we learn something about quantum gravity? Yes.
Yeah, but that's the same related story. So yeah, if you know the CFT, you can. Yes. So in principle, yes. So you could think of this. What would be the black hole in this from Young-Mill's point of view? What's the that, what's that, and yeah, in principle, but it's much harder questions, like the questions about some anomalous dimensions or even some correlation functions, but at finite temperature. So at zero temperature, finite temperature is much more, it's harder, but plus black hole is a kind of different phase. You need to have a non-trivial state in the bulk, like coherent state in a way. Coherent states of these gravitons, which are dual to single traces, single stress tensor operated at the bulk.
Any follow-up on this question?
I have follow-up. So thinking about the bootstrap, if I have effective field theory on ADS and I don't know its stringy construction, but it's maybe some supergravity. If I apply the holographic dictionary anyway, can I use bootstrap maybe to reconstruct some parts of the CFT and understand if there is a CFT dual that maybe I'm not able to construct directly?
Yeah, that's a very good question. In fact, there were recent papers which what they do, it's easier to try to say what they are doing rather than how this relates to your question. So suppose we consider, say, N equal 4 super Young-Mills theory, and we can somehow compute correlation functions of stress, let's say 4 stress tensors in that theory with high enough order. So then we interpret them as certain scattering process or correlation function of gravitons in the bulk in ADS5. And then we try to take flat space limit. And flat space limit means basically you need to specify what would be your momenta, etc., and take a certain limit of radius. But you end up with scattering amplitude of gravitons in flat space. So starting with Young-Mills, you can actually reconstruct scattering amplitude in flat space. And that will give you analog of, say, Veneziano amplitude, Shapiro-Virasoro amplitude in string theory, if you include enough corrections. So it will include string corrections. So in a way, yes, so you can actually get information about bulk string theory from CFT in that way. But you need to know results in CFT, which are kind of exact in N and lambda. So to go beyond just supergravity, that's essentially.
Any alpha prime?
Yeah. Yes. The point is you will need to decide what you keep, in what you expand, and what you. But these correlation functions some of them can be fixed from localization. Some terms in this expansion, but it will be like low energy expansion, for example, to some order in curvature expansion. But the coefficient would be exact in, say, string coupling, something like that. And that's some things which they were trying to check is like S duality, SL to Z invariant. So these coefficients, that's what Mike Green was doing earlier. Like R4 term should have certain coefficient as a function of string coupling a dilaton, which is consistent with S duality. And that was, yeah, that's what you can get from starting from the boundary if you have some localization result for some correlator, and then translating into statement about scattering amplitudes in the bulk, in the flat limit, and trying to make prediction for string theory, even at finite coupling. So it's going beyond what you can do.
Sorry, I did not get it. Is it like 3-level in GS, or
No,
you can also really all
the whole point is that for this correlation, for certain observables in the CFT, you have exact results from localization. And the technical progress was to realize that in certain results, which you can get from localization, can be translated in certain statements about correlation functions, even of four-stress tensors, which would be due to supergravity, to four-graviton scattering in the bulk. And that gives information about G-string dependence to all orders, effectively. In
GS and in alpha prime.
In GS, alpha prime, you need to decide how many terms you keep in low energy expansion. So they were still expanding and matching the low energy.
Some order in alpha prime and all orders in GS.
Yes.
Okay, thanks.
There was recent papers by Aldai. They were trying to get the full, they were trying to get the matching to Shapiro-Versor amplitude, in which you will have Reggie behavior. So yeah, the answer is that in principle that should be possible. Yeah.
Hold on the previous thing that you said. So you said what would the black holes theory and stuff. Actually, recently, Raj Gopal and myself, we argued that the color glass condensate in QCD is like a black hole state because it has all the properties, the entropy, thermally, and so on, even phase time. So could you have such a state in your?
To color glass, you mean some condensate of F menu?
The color glass was not. The overall state, actually, you can observe it at the Terra in Daisy. So there's a state of gluon. So our interpretation was that it looks like it has all the properties.
Yeah, but my question: what's the definition of color?
It's a high saturation state of gluon.
But it translates in certain non-zero correlation functions, or what correlators of F min. I think that depends on certainly. It depends on asymptotic freedom and on having confinement. I'm pretty sure it should be the case, but this is non-confining theory. Yes, in principle, yeah. But are you sure you don't need scale, because this is conformal theory?
Forms way above the confinement scale.
Above.
It's like a collective effect in a perturbative regime.
Okay. Maybe that's interesting. Yeah. I don't know any discussions of that kind of discussion. Oh. Yeah, that would be interesting. Yeah.
Other questions or follow-up? Paolo.
In ST, you model the gauge theory living on the brain is as beta function 0.
Those brains are just wrapping the internal circles. There's not really a gauge theory because we don't have any flux on it. These are just a billion. These F mu nus are the U1s in the DBI action, and that's the effective action. So
if you have more brains, you don't get
No, because because they are just geometric charges. They are these branes are just wrapping cycles, but there's no dynamics on them. That's the difference from the case where there are fluxes, but then those fluxes will give a cosmological constant in the low energy theory. If
so the rounding that you were talking about is not connected with the rounding of the carbon copy.
No. That so the nice thing about black holes is that they provide the running by space-time. So the radial coordinate in space-time provides. It's not really running. It's just moving in parameters in moduli space. It's probing the moduli space through the gravitational solution, but it's not a gauge theory running. So sorry if I use that the term.
But in the gauge theory, you cannot see this around.
They don't have a gauge theory dual because those I was talking about are in Minkowski. One can construct something analogous from ABJM, looking at the n-equalate effective field theory in ADS4. One can have a truncation to something similar to the STU model, but there one remains in the comfort. The dual theory is just a supersymmetric theory in everything is conformal, and it's just a matter of identifying supersymmetric states with those charges. And in that case, yeah, the gauge theory on the brane is ABJM. So thanks.
Any follow-up? Or new point? Last chance? Okay, if not, then let's thank again Arkady and Alessandra for talk and discussion. We are going for lunch now.